In this lecture, we will be learning about the topic of Taylor's theorem. Recall the definition of Taylor's series. If you're given a function f that has derivatives of all orders through some interval containing a, the Taylor series generated by f at x equals a is the following series, the first few terms written out this way. We then define the Taylor polynomial, which is a partial sum of a Taylor series, where we stop at the term of order k. Taylor's theorem tells us that with a function f that has derivatives of all orders in an interval I containing a, then for each non-negative integer k in each x in I, we have the following equation. F of x is equal to that kth degree Taylor polynomial plus a corresponding error term we call r sub k, where r sub k looks a lot like the first term that we omitted. Everything in this term is the same as the first term omitted, with the exception of this c. So we don't know a priori what c is, but we know where it lives. We know that it's in between a and x. We can use this in many different ways. We will see a couple of those explored in this lecture. One of the ways we will use it is another part of Taylor's theorem, which says, in that same scenario, if the limit as k goes to infinity of that remainder term equals 0 for all x in I, then f of x is equal to its series, its Taylor series, for all x in I. So the Taylor series converges, and it converges to its generating function f of x. And intuitively, the way we can imagine that is that f of x being equal to p sub k of x plus r sub k of x, as we let k go to infinity, letting k go to infinity is effectively saying keep increasing the degree of your Taylor polynomial. When k goes all the way to infinity, the Taylor polynomial becomes the Taylor series, and if this remainder term goes to 0, we get that f of x equals its Taylor series when we take this limit. So this Taylor polynomial as k goes to infinity approaches that Taylor series itself, and the remainder goes to 0. That's the essence of Taylor's theorem. We saw in the introductory lecture on this topic an example where we took a function f of x is 2e to the cosine x plus 2x, and we constructed the first three Taylor polynomials at a equals 0, sometimes called the Maclaurin polynomials, and we got the following results. And the reason we are revisiting this example is to look at the graphs. So this is the graph of our original function. F of x is 2e to the cosine x plus 2x. And we see that if we think of this as being used to approximate the function near x equals 0, so think of using an interval, for example here say -1 to 1, at which 0 is the center. If we use the 0th order Taylor polynomial, we can see that near 0, this is a good approximation. If you really zoom in, it gets better. If we go one more step and use the first degree Taylor polynomial, which turns out to be the tangent line at x equals 0, we get an even better approximation near 0. And if we go one more step and use the second degree Taylor polynomial, we get an even better approximation. And the idea is the higher the degree of the polynomial, the better the approximation near 0, near A. And if you go all the way, these Taylor polynomials will snap into the Taylor series, which will match the function exactly. We'll use this theorem in the following capacity. We talked about, in a previous lecture, the Maclaurin series for cosine of x, and we derived this result here. We argued that using the ratio test, this series was convergent. And we can use Taylor series to show that it actually is equal to cosine of x. And so recall, if we write out the first few terms, this worked out to be 1 plus x squared over 2 minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, so on and so forth. So to actually prove this, let's take a generic Taylor polynomial from this Taylor series. And so what we're doing here is adding up the terms up to order, the 2k order term. And we're using 2k because it's more convenient for cosine, because cosine only has even powers of x appearing in its Maclaurin series. So written out, this would be 1 plus x squared over 2 minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, all the way up to that last term, could be a plus or a minus, which would be x to the 2k over 2k factorial. When we think of this as our approximation to cosine of x, we cite Taylor's theorem to say that cosine of x is equal to that approximating Taylor polynomial plus the corresponding error term, r2k of x, where r2k of x is of this form. So we see it looks a lot like the first term left out. The first term we would leave out would be when the order is 2k plus 1. A is 0, and we're evaluating this at c for some c between 0 and x. So we don't know c, but we know it's between 0 and x. Now, we rearrange that equation that we had here. So rearrange this equation by subtracting p2k from both sides and take the absolute value, and that is our error. And we're concerned with error. The error of our approximation, again, you want to think of this as we're using p2k of x as an approximation to f of x, or in this case, cosine of x. So the absolute value of the difference between the actual function we're after and its approximation is the error. And so let's take a look at the size, the absolute value of that error. We rewrite our error term here. And the question becomes, can we find an upper bound on this error? So anytime you're doing an approximation, it makes sense to look at the error. Here, although we don't know what the error is because we don't know c, we can still say something about how big this error can be. We want to find an upper bound for it, a worst case, because your error can never be worse than the worst case. So let's simplify things a bit. We take this r2k term, and we note, first of all, 2k plus 1 factorial, that's positive, so that can come out of the absolute value sign. And then the absolute value of the product of the function evaluated at c and x to the 2k plus 1 can be written as the product of their absolute values. And we know something about this derivative. So that derivative evaluated at c, because we're working with cosine of x, its 2k plus first derivative has to be plus or minus cosine or plus or minus sine. What we know about sine and cosine is their range is minus 1, 1. So that means the absolute value of this top term here can be at most 1. And the rest we retain. And we can bring that absolute value sign inside if we like. So this gives us an upper bound on our error. Well, with that upper bound, so this is less than or equal to, we just argued absolute value of x to the 2k plus 1 over 2k plus 1 factorial, we can now notice that as k goes to infinity, what we have here is a race situation where we have a polynomial term in the top and a factorial term in the bottom. And we learned when we studied the ratio and the root tests that as k goes to infinity, this polynomial term, it doesn't matter what it goes to, whether it goes to 0 or infinity or something in between, this factorial term goes to infinity so quickly compared to the polynomial that as k goes to infinity, this term will go to 0. So we know that the limit as k goes to infinity of the absolute value of our error term is less than or equal to the limit as k goes to infinity of this absolute value of x to the 2k plus 1 over 2k plus 1 factorial, which we're making the argument is 0. So again, if we look at our previous work, specifically when we looked at the ratio test, we saw that this was the case, which is exactly what we wanted. Recall the idea was that cosine of x was equal to p2k of x plus r2k of x, and we just argued that this r2k of x is going to 0. If its absolute value is going to 0, then it itself is also going to 0, which is exactly what we wanted. This implies that cosine of x in fact equals the Taylor series that we were looking at. Sum n goes from 1 to infinity of minus 1 to the n x to the 2n over 2n factorial. And this completes the proof. And we summarize that not only for cosine of x, but for sine of x and e to the x as well. Similar approach will show the same result for sine of x and e to the x. So we now have it officially that cosine of x, sine of x, and e to the x can be expressed, that's a division, as these Taylor series. We can often use these in some very, very handy ways when we're constructing Taylor series for other functions. For example, suppose that we're asked to find a series representation of sine of x squared. Well, we already have that sine converges to its Taylor series, its Maclaurin series here. But notice we've written it in terms of u instead of x. And we know this works for all u in the real numbers. So let's try and use this to create a series for sine of x squared, and we note that we can call x squared u. And we can substitute that in for these u's in our series. If we do that, we have that sine of x squared is the sum, where n goes from 0 to infinity, of minus 1 to the n. And then we have our u, which is x squared, raised to the 2n plus 1 over 2n plus 1 factorial, which we can simplify using our rules for exponents, where these exponents for the x term multiply, and we get x to the 4n plus 1 over 2n plus 1 factorial. Another way we could see that, you can work directly with the sigma notation, or we could work with the terms as they're written out and then figure out how to write it in sigma notation. So we could also write this as plugging in this x squared for these u terms here. So we could write this as x squared minus that u cubed over 3 factorial, and again that u is our x squared, plus our u to the 5 over 5 factorial, minus our u to the 7th over 7 factorial, and then we could use our rules for exponents to simplify this, where we would get x squared minus, here we see the exponents multiply, x to the 6th over 3 factorial, plus x to the 10th over 5 factorial, minus x to the 14th over 7 factorial, so on and so forth. And then from this, we can figure out our indexing to write it in sigma notation here. Either way, the goal is to get to this sigma notation answer, because when you write it this way, you are writing an expression that includes all of the terms. And we want to think of writing it this way as seeing the pattern. But this is a very handy way to compute and construct Taylor series without going through the definition of Taylor series. The definition of Taylor series to construct this for sine of x squared would be quite complicated, because think about as you start to take derivatives of sine of x squared, you use the chain rule, and then that's going to result in uses of the product rule. And so this is a quick and simple way, compared to using the definition of the Taylor series, to find a series representation for something involving sine. We can do the same for cosine. We can do the same for e to the x.